How's everyone doing? Tired? Have any of you started on the next assignment? Not yet. It took a look at it. Some people took a look at it. Yeah. And
There's a lot of math words, and I was like, I don't have the energy to look at this.
yeah.
Yeah. I'm sure it's fine, but it's scary when you see it.
Do ask any questions in the office hours. Ask, post on Piazza. We're here to help. We're really here to help. Like I have office hours on Thursday for 2 hours, and sometimes like I get some people, but it's still like the last half an hour has always been free. So you have opportunities to come and ask for clarifications. I'm trying to make things as clear as possible in the class, but I know it's not possible for everyone to get everything from the straight shot. But do use these opportunities. And I know you have other courses as well, so kind of it gets tricky, but yeah. Let's see, what time is it? Oh, okay. So I think we can get started. That works. I hope people can hear me on Zoom. Do give a yes or no on the chat. Yes, perfect. Great, thank you. So do also, for people on Zoom, feel free to ask questions. You can even unmute yourself and you can unmute yourself and ask any questions. Like I hear in the headphones, and I'll repeat a question for the class, so for everyone in class to hear it. So I know it's kind of challenging doing a hybrid format, but I thought I'm trying my best to sort of get to accommodate everyone here. I have two quick announcements to make, which I just wrote now on the slide. So the first thing, so the midterm will cover everything up to and including reinforcement learning. So the lectures today. So we'll do reinforcement learning today and next slot. So next week on Tuesday, and on Thursday we'll do a whole class with exercises. So I'll prepare exercises and we go through them on the blackboard, and we kind of like. And even if we finish things early next Tuesday, we can even start the exercises from next Tuesday. So we can even like have maybe even a session and a half. Let's see. I have a feeling we might finish halfway on Tuesday next week with the RL. So yeah. Yes, and we do have. I think we will have a discussion session right next week. One discussion session given also by the TAs before the midterm. So again, the same thing. We'll be just going through exercises for that potential exercises that can help you solidify the concepts and help you with the midterm. Okay. So if you remember, in the last class, we started talking about the idea of reinforcement learning and how we have an agent that acts in an environment, and the agent gets rewards when it reaches certain states in the environment or does certain actions. And the goal of this paradigm is for the agent to maximize the rewards. So it's trying to take the actions that maximize the rewards in a particular environment. This is the paradigm. So it's much more interesting than what we've been doing so far, where we had just a static data set. We didn't have an environment. It was just like a set of data points that did not change. But now we have an entire environment that can give us data points. Can people hear me? Yeah. So that's what we have. And 1 second. Yeah. We saw we were talking a bit about some examples in real life of how you can do this. You can do these kinds of what kind of like phenomena in real life we can model with reinforcement learning paradigms, and we started like seeing a bit these videos of a robot that is running a reinforcement learning algorithm that's training it how to walk, how to do the movements, And you can think how these movements for a robot, they're very complex and very complicated. You have to move an arm, like a leg, for example, forward in a particular way. And even that movement forward is very complicated because it has articulations. For example, it has 2 or 3, and that means you need to change certain angles in those motors and so on. So it's a very complicated process to get these movements correctly. And so we saw these examples, and I'm not going to show it again, of how initially it was not performing well, but after training it started learning, and it was moving much faster and much more efficiently without slipping off. This is freezing a bit so I'm skipping this because we saw it last time. One sec. It's still frozen because of the size of the movie. Okay, so I wanted to show you another video. And another setting. Did I skip 2 slides? Sorry, it's kind of going slow. Okay, so this is another robot that basically has only 2 wheels, and it has two actual arms that can lift itself up. So it actually has multiple types of poses it can be in. For example, it can stand upright and basically balance itself like that, or it can also use these arms to lean itself forward or even backwards and to lift itself up. So let's see how that works. So you see now it's lifting itself up, and then it can move forward and backwards and keep itself in equilibrium this way. It can rotate, again move forward, backwards, and lean on the arms, stand down again. And look how it is robust. Even if you push it in particular directions, it still stays there. Again, even if you push the robot, it doesn't lose its balance and stays correctly. And so this is the same robot and here I'm showing a simulation. This is in a simulated environment. This is the same robot now in a simulated environment. How it is trying, for example, in this case on the right-hand side, to do a rotation, to rotate it like around its axis and learn what is called a policy. How do you take these actions so you basically rotate the robot around to do like a 180 degrees rotation, for example. So it has to do this complex set of actions of changing these kind of like hands in the front like this. So sometimes the reason why I wanted to show this is because sometimes these simulated environments in robotics can be very, very helpful for learning how to do these kinds of complex tasks, complex coordinated movements. So these simulators are very popular and widely used. Although they have some kind of gap with reality, sometimes what you train to do in a simulation might not work exactly as you planned in reality, but they are still very useful. And this is another policy on the left side, where the robot, again in a simulation, now is trying to move forward. And now without using the wheels, just by using the arms, you see it can learn how to push itself like that to move forward. So it's so each of these we'll call them like different policies. This is a policy that helps you move forward. This is a policy that helps you rotate around your axis. So moving on. That's another example of the same robot, again on the putting it now on the hardware again. So we train the policy, for example, of how to move forward in a simulation, and now you put it on the hardware, and this is how it works and what it does. Again, it's trying to actually use the arms to move forward. Any observations, any questions, any remarks? Okay. So reinforcement learning is not used only in robotics. It's also used in many other settings. For example, games. So this is an example of a game of poker in which people from Carnegie Mellon University, CMU, developed an algorithm based on reinforcement learning called Libratus that basically was able to play poker, so Texas Hold'em, really well. And so it's used a lot also in games because, again, you have an environment, which is that particular game. You have, like, you can take actions, what card you want to put down, and so on. And in the case of poker, it has also been very popular. For example, one of the most successful stories was that actually, like, using reinforcement learning, we've been able to be the champion of Go a few years ago. So AlphaGo was a system developed by Google DeepMind that was able to win against the best Go player in the world, the world champion of Go. And I have to say Go as opposed to chess. So Go is a game kind of similar to chess, but it's much more complex. As opposed to chess, the state space of Go is much bigger. So for each movement, you can do many more. We have many more possibilities than you have in chess, for example, and on the order of 10 to 100x more movements. But as a result, that's why it was much more complex, and it was one of the sort of like final frontiers in terms of the board games that the computers could not beat up until recently. Computers could not beat human players. And of course, it has been used in many other things. So I haven't shown here, but for example, the same team at Google DeepMind also, for example, beat some of the best players at StarCraft. So again, they made these kind of like game agents that could win against champions of the game. So and StarCraft, for example, is supposed to go is an even much more complex game, much more complex environment. You have impartial information. You don't observe the entire scene. For example, you don't know all the state. Like here in Go, you observe the entire board, but in StarCraft, for example, you don't know whether the enemy units are, for example. So you have much more incomplete information that you have to infer using these sophisticated techniques. So reinforcement learning, what I'm trying to say is it's a paradigm that is very broad and applicable to many scenarios. So let's see how can we implement reinforcement learning. So in the first the key concept you have to understand is that of the Markov decision process. And the Markov decision process is generally like we have to have an agent that lives in an environment. And for example, the environment could be like this. For example, like we can take the idea of a stochastic grid world. So we have our little robot lives in a grid. So it can only, for example, be in one of these squares. So we have 3 by 4 squares. We have one square here that cannot be occupied. Let's say that there's a block here, so the robot cannot take that square. So we can either go like this or like that. And there's 2 states here that have rewards. So one state has a +1 reward, and another state has a -1 reward. So of course, the goal of the game is to maximize the reward. So you have to reach this state and try as much as possible to avoid this state. So to not go there. And so that's our environment. This is our environment. Now we have an agent a robot that starts from here, and it can take actions. So the actions it can take are, for example, to go north, to go south, to go east or west, for example. So at each point, it can only take one of these actions, up, down, left, right. And there's a big rewards that come at the end. And the goal is to maximize those rewards. So in this case, we have a +1 reward. And another key concept I want to stress is because we live in a probabilistic world in this case. So the actions can be stochastic. For example, the robot can try to go north, but 80% of the time it actually ends up going north. sometimes maybe 10% of the time it ends up going east and 10% going west, for example, if it takes a north action. So sometimes even though you try to do a particular action like going north, you can end up still in another state that is not north, it's actually maybe east, for example. So we'll assume that 80% of the time it actually ends up going north, for example, and 10% of the time it will either go to the left or to the right. And the same for all the actions, the same for south, the same for east, same for west. It can end up, deviating. And this is, again, this is a block that it cannot be occupied. So this is our probabilistic state space. So again, 80% of the time it goes north. Sometimes it can end up being left or right. So this is the difference between a deterministic grid world, where you always end up in the state where you want to. If you take an action like going north, you always end up in that state, versus in a stochastic one where sometimes you can, even though you go north, you can sometimes end up going to the left or to the right. So here, and you can end up, for example, falling into a pit and so on. So you're trying to kind of like adjust your probability so that maybe you're not too close to a pit. Even though you don't want to go to the pit, sometimes you don't even get close to it. So because by chance you can end up falling into there. So that's our setting. So Markov decision processes. So how do we formalize? How do we mathematically formalize these concepts into a mathematical structure that allows us to do inference and model it properly? So a Markov decision process is defined by several elements. So first of all, we have a set of states, S. So the states are basically where does the object, where is the robot in the maze? Is it in this state, in the 1-1 state, or 1-2, or 1-3, and so on? So in our case, it will be just where is the robot in the maze. We also have a set of actions, A. So the actions will be going north, going south, going east or west. And in particular, we also have a transition function. So T of S, A, S prime, what it means is that if you are right now currently in state S and take action A, then you will, this will be the probability that you'll end up in state S prime. Or put otherwise, what's the probability that you end up in state S prime given that you start in state S and take an action A? So here this would mean, for example, what's the probability that you end up in 1-2, in state 1-2 here, given that you start in state 1-1 and you take action to go north, for example? What's the probability? And that would be 80% from what we said before, for example, because you generally 80% of the time you actually end up there. So it will be the probability that action A from state S will lead to S prime. And we can also write it like this. So P of S prime given S and A. The probability that will end up, again, I'll say again, the probability will end up in state S prime if we start in state S, and take action A. And it's also called the model or the dynamics of the environment. So, and we also have, apart from this, we also have a reward function, R of SAS prime. So a reward, what it basically means is, if we are in a particular state, S prime, and we came from S and took action A, what is the reward we get? But often we usually simplify it, and we just say what's the reward that we are in a particular state S prime. So we don't make it dependent also on the action or on the previous state, the reward. So because that kind of complicates things. So often we just say what's the reward that you are in state 1-2. For example, so here would be 0 reward. You don't get any reward. This would be 0 reward. And here you get a reward 1. And here you get a reward of -1. So most of the states here will have 0 reward apart from these two. So that's what the reward function models. We have a start state, which is 1-1 here, and we have a terminal state. So terminal state would be one of these two, either +1 or -1 in our case. Do we have any questions? Is it clear? Yeah?
So the states are just the coordinates.
The states are the coordinates, yes. So the states are the coordinates. Will be 1, 1, 1, 2, 1, 3, where the robot is. What are the actions again? Let's recap. What's an action? What's a potential action? Direction, yeah. Going north or south or east or west. What's the transition function? What does that mean? Want to hear? Yeah.
The probability of
the probability of
the agent from one state to another state.
The probability of the agent going from one state to another state.
Yeah.
Yes. By taking a particular action A via a particular action.
Yes.
So the probability of transitioning from state S to S prime via a particular action A, via, for example, going north. That's the okay, got it. So I think it's all clear for everyone. And the reward again are these plus ones and minus ones. So yes, and MDPs, Markov decision processes, are non-deterministic search problems. They so again, because we live in a probabilistic world, this we will this is what this means. We basically it's not a deterministic plan, and basically even though you try to go north, sometimes you can end up going west with a small probability. So we have an interaction loop here that is happening. So we have the robot, we have the environment, we have actions, we have states, and we have rewards. So there's a loop. So initially in our environment, our robot starts in state S, and then decides to take an action A. It receives a reward, R of S and A, and then it transitions to another state S prime, according to this probability distribution T. So this is it's called a transition distribution. That's why it's called T like that, because it's transition from state S to S prime. Then the agent chooses another action B, receives a reward, S prime and B, for example, and then would transition to another state of S prime, B, S double prime. So we move to another state S double prime, and so on. So it's also a loop. You always take an action, end up in a new state, you collect a reward, take another action, end up in a new state and collect a reward, and so on. Yeah, all clear? Now we have to understand we were talking about Markov decision process, but what does Markov mean, and why is this an important property for the model to have? So the Markov property is a property that says that your probability of ending in a new state S prime. Actually, don't look at the equation. Don't look at the slides. Just look at me. So the probability of going in a new state does not depend on the past. It only depends on the very last observation. That's what the Markov property means. So it means that even though you were in many states in the past, S0, S1, S2, ST minus 1, ST, and so on, your probability of reaching a new state only depends on the very last state and not on the past. So it only depends on the present and not the past. So the present is the only thing that matters for moving into the next state. The past does not matter anymore. That's what the Markov property means. And it's a property that was developed by a mathematician, a Russian mathematician called Andrei Markov, and it's very, very useful and it's you see it in many concepts. How many of you have heard of the Markov property? Have encountered it? Some. Okay. Yeah. It's very important because this property ensures tractability, ensures that our model will be tractable for us to infer. Because look at this equation here. We have a huge number of conditional states that we have to model otherwise. Like imagine if the robot took 200 actions, 200 states in the past. That means we have to model a huge distribution or with 200 conditionals, and so on. So that's even if each conditional is a binary, for example, state, even a simple binary state, it will still be 2 to the power of 200 types of elements we have to estimate. So that's a huge number. Whereas this is much much easier. You simply, if it's a binary state, then you have two states here, 2 elements here, 2 elements here, maybe 2 actions. So then you have 2 by 2 by 2. So we have an 8 values you have to estimate. So much simpler than 2 to the power of 200. So it's very important. And you encounter this not only in reinforcement learning, but the Markov properties. I mean, it's used in Markov chains as well. So when you do like statistical learning, also in if you take some more advanced machine learning courses, you'll learn Markov chains and like MCMC sampling. It's also used in stochastic processes. So if any of you will ever take for example, some courses on stochastic processes, again the same. You have the Markov property there, where a process can change to other states, and it's only depending on the present state. So it's encountered in many disciplines, not just in reinforcement learning. So how do we solve the Markov decision process? How do we actually learn a policy? So in particular, what we want to do is to learn a policy pi. So the policy, what it tells us is what actions we take when we are in the environment. So this is what a policy looks like. It shows us that when we're in a state 1-1, the best action to take is to move north. Same for 2-1. The best action to take is to move north. Here, the best action to take is to move to the right, and so on. Notice how, for example, when you're in state 1-2, the best action to take is to actually move left, and because otherwise you get close to the -1 state, which could lead to failure, for example. So the policy tells us given each state in the Markov, in the environment, what is the best action to take in that particular state. That's what the policy tells us, and we want to learn this policy. Once we have a policy, the robot can take a decision, can take decisions, can make a plan as well. Can make a plan and say, if I'm start from here, I make a plan, so I go here, then here, then here, and this way I reach my reward. So it's important for decisions and for planning. Yes, and the way we will optimize the policy is by maximizing the reward. That's how we will do it. Any questions so far? Yeah?
When it reaches the reward, how does it know it has taken the best possible path?
How does the robot know that it has taken the best possible path?
Because we choose the best path available at the situation, so it's like a greedy approach.
Yeah.
So is it possible we miss the best path and just take the longer path instead?
Yeah, so our colleague is saying what happens, sometimes we make greedy choices and we take, and sometimes we might miss the best path. What happens in that case? So that's a very good observation. We'll see how, with what we'll do, it's actually not, we have a solution that is not a greedy solution. Actually, we'll use something called the Bellman equations, and those will do what is called like an iterative inference. Sorry?
Is it like
Kind of. No, it's a bit more complex than that. It's not a breadth first search. Yeah, we'll see shortly. It's like a global optimization scheme where you do an iteration between policies and values. We'll see very shortly. But right now we're trying to define some objectives. We're trying to find a policy. Like we'll see, and you can also do it with greedily, yes. And but there's better ways to do this. Any other questions? And I'll come back to that again. I'll show you how we do that. Any other questions? Is it all clear so far? Yeah. So let's see an example. What if we have a card example? Like we have like a game of with these cards, and we call it high-low. And basically, we have three cards, 2, 3, and 4. And we have an infinite deck. And in general, in our deck, we have twice as many 2s as the 3s and 4s. So the game starts as follows. Like the rules are as follows. So we start with the card 3, and then after each card, we say either high or low. And then if we were, and then a new card is shown, is flipped from the deck. And if the new card is higher, if you guess right, if it was higher than the 3, then the game moves on, and I keep on playing. Otherwise, if it was wrong, then we stop. So that's the game. The game ends. And if you're right, you win points, again shown on the new card. So you have to decide beforehand if, for example, if it's a 3, if it's going to be higher, the next card will be higher, and you have to guess right. And
What if it's the same value?
if it's the same value, that's fine. Also, that will keep you. You don't win any points, but the game doesn't end. So that's a simple game. But the reason why I'm showing this is because so we'll see shortly. We'll draw the decision tree in the next slide. But let's see what is our model. So our states are 2, 3, and 4. Those are our states. Our actions are high and low. We're trying to predict if the next card will be higher or lower than our current card. And this is the model transition probability. So this is the transition probability T of S A S prime. So here's what this means. So if the current card is a 4 and we say low, that means we guess the next card will be lower than a 4. Then this is the probability of getting a 2, given this is a half, because we have twice as many 2s in the game. Probability of getting a 3 on a 4 is a quarter, because we have there's fewer of these. The probability of finishing the game in given a 4 and you guess low is 0, because you always get a lower card. You always get at least lower or a 4, at least 4 or lower. So it will be 0. But imagine if you're in a state 4 and now you say high, then basically you can never reach a 2 or a 3. This will be 0. If you get a 4, the game continues with the probability or a quarter. But or if it's a lower card, then you can the game finishes, because then if you get a 2 or a 3, then essentially the game is over, because you guess wrong. So you said it will be higher, but actually only 4 can be at least equally higher as the other one. So and you get and the rewards are basically the numbers shown on the card. So you get a reward of 2 if you guess the 2 correctly, and 3 and so on. So that's the reward numbers shown on the card that you draw. So if we start from 3, this will be our state space. So we start from 3, then we guess we have either low or high probability, and then we get these states, and we've seen a bit, these are called Q states. Now we have like a card and an action. We have a state, so state which is 3, and an action which is low. And then given we have a state and an action, that this can take us to a new state, to a state of 2 or 3 or 4 and so on, with a certain transition probability. So we can transition to these other states with these probabilities. So we can go to this branch with the probability 0.5, and then we have a reward of 2. We go to this branch with a probability of 0.25 and the reward of 3, and so on. So we get a transition and a reward. And if we get a 4, then the game is over here. So in this case, the game is over. We don't get any more rewards. And we keep doing this again. We keep going down also on these, on and on. So this is what is called the computational graph of the game, or the state space, or it has multiple names. But that's the general idea. So in more abstractly, what we will have is that we have a particular state in the tree, or the computational graph, and we take an action A, and it takes us to this intermediate node SA, which this is called a Q state. So it has not only a state but also an action associated to it, and a Q state can take us to a new state S prime. We can transition to a new case, and this is we call it transition model, and again it's called T of SAS prime or like this. Does this make sense? Yeah. So yeah, you have a question, yeah.
What's the point of the Q state? Why just not go from S to S prime?
That's a good question. What's the point of the Q state? It's we'll see shortly. Actually, you can do in the Bellman equations. We can infer the values of Q states, and if we infer the values of Q states, we can do it a bit more efficiently. If we do the updates. So what we'll do, we'll at the level of the blues basically. And we'll have a level of blues here, another level of blues further down. For example, when we estimate, we kind of like infer at those levels instead of the red levels. And it will be a bit more efficient like that. That's why they defined. But yes, I know it's a bit, it can be a bit superfluous, but that's the reason why they define like that. Any other questions? Okay. So in order to reason about rewards and these and how we can maximize them, what we also need is the concept of a utility, and generally in general what it means is that it also means, for example, a classic example in economics is the utility of money, for example. So it's and it's nothing to do with the slide. So it's, for example, you have $1,000 and could give you a certain utility, maybe 1,000, for example, 1,000 points of utility. But if you have like $1 million, it might not give you 1,000,000 points of utility, or like if you have $1 billion, because at a certain point you don't know what to do with the money, for example. So it has less use to you, basically, less utility. So people have been studying this concept in economics for a while, and how the utility of money is not linear. It sort of starts plateauing after a while, because what's the matter? What's the point of having $1 billion or $10 billion? It's almost the same. So basically, so that's the idea of utility. It's like it's not the same as the quantity of the rewards. Like, so of course, like in the case of money, so 1 billion is 10 times less than 10 billion, but in terms of utility, it might not be. It might be almost as equal in terms of utility to one individual. So somehow the same thing happens in these Markov. Actually, a few more things, and even in economics, the same $10 you have now are worth more than $10 you have in a month. So there's a time utility as well. So the utility of money now is higher than the utility of money in a year or into the future, because you can invest that money and so on. So it's the same idea also here in MDPs with utilities. So if you get a reward later on, like, or if you got it will have less utility, and vice versa. If you got a reward in the past, way in the past, you kind of forget about it, and you get more utility if you get current rewards. So we'll see this very shortly. It's called discounting. So what in order to formalize it, what people are saying is saying that there's this concept of a stationary preference, and what this says is that if you have a certain sequence of rewards, R, R0, R1, R2, and so on, that is preferred to a different sequence of rewards, R0 prime, R1 prime, and so on. So this symbol means that this quantity on the left side is better or preferred than the one on the right-hand side. Then if we simply take out one reward, like the first reward, the first R, then the sequence with the rest of the rewards still holds. Then even if we take the reward from today, for example, the rest of the rewards are still going to be preferred to the other ones. This is what stationarity means. And it's kind of like a formal way to start sort of like encompassing a whole class of functions that could be utility functions using a property like this. And there's a theorem that says generally that if you have this property, then there are generally only two ways to define these utilities. And one way is to do an additive utility. So if you have a utility of multiple rewards like this, would be just add them up together. if you have a utility of a sequence of 3 rewards, it's just adding up the 3 different rewards. Or you can discount it. So you have discounted utility. So you discount by a parameter gamma the utilities that will happen in the future or in the past, for example. So in case of money, the money is much more useful now than in the future. So you discount the ones in the future. Then if you get $10 now, it's much more it's more valuable than if you get $10 in a year. Or in the case of the robots, it's the other way around. It's in the case of MDPs, we'll have that the rewards from the past, we'll start discounting them. So with this parameters gamma. So this will form a geometric series. It will start with gamma, then gamma squared, then gamma cubed, and so on. So it will form a geometric sequence that has, in general, it has some nice mathematical properties, and we'll see shortly why that's very useful. Any questions here?
So R0, R1, R2, the states, like the rewards which we got in the state 0, 1, and 2.
Exactly. The R1, R2, R3 are the rewards the robot gets in each of those states, for example. Yeah. So one problem we often encounter is the problem that sometimes in these MDPs we can get infinite utilities. We can get an infinite number of, well, sort of, after we do these policy iterations and value iterations, we'll see sometimes we can reach infinite utilities, because if we have these states that keep on accumulating utilities, you just keep playing on and on and on, and you accumulate an infinite number of utilities. So, and sometimes, like 1 infinity is the same as 2 infinities, and so on. So basically, then it becomes hard to reason about these quantities. So some solutions are to basically, for example, have a finite horizon. So basically, we terminate the episodes after a certain number of steps, after t steps. Or we can give non-stationary policies where the policy pi depends on the time left and so on. Or we can do, for example, discounting with gamma, what we saw on the earlier slide. So then we discount the past utilities. So if you're given a sequence of utilities R0, R1, R infinity, then this would be the sum from t equals 0 to infinity of gamma to the power of t times RT. So these are the utilities RT. These are the rewards, sorry. But they are discounted by the parameter gamma to the power of t. And t is the time step in the future, like how much 5 steps in the future, then we discount by that, by that much. Gamma is between 0 and 1. So it's always, in future time steps, these will be discounted even more. So, and if you do a geometric series computation, then this will be less than or equal to the maximum reward divided by 1 minus gamma. And this is simple to have any of you seen this geometric series and why it leads to 1 over 1 minus gamma? How many of you have seen that? Yeah, some. Yes. So let me. The key idea is that, and I'll do it quickly on the board, but this is kind of like coming from. I mean, it's yeah. Some of you might have seen it in late high school, or like in some courses in math. So essentially, if you do a series like Sn is equal to 1 plus r squared plus let's do gamma, because we have gamma here. 1 plus gamma squared, gamma to the power of t. Yeah. So this will be st in this case. So what we do in this case, we multiply, we do gamma st. So we multiply this by gamma, and this will be gamma plus, so I can do them one by one. So this will be gamma plus gamma squared plus gamma cubed plus gamma to t plus 1. Yeah, and then you can subtract this from that. So you do st of gamma minus 1. So I subtract this from that, and this will become, so this cancels with this cancels with this, and so on. And this will cancel with that one. So this, like this, they match. So this becomes gamma t plus 1 minus 1. Roughly, if I haven't made any mistake. Does that make sense? So, so then of course you can do st equals gamma t plus 1 minus 1 over gamma minus 1. So that's the factor gamma minus 1 over minus gamma minus 1 that appears there. And R max is basically saying this will be always each of the RTs. It's as if you know that this will be smaller than or equal to an R max. So you do first the inequality, and then you apply that thing. Yeah.
So right here it says in the summation it says gamma gamma to the t. Never mind, I was just reading it wrong.
Yeah. So the t is with gamma. So the gamma factor you raise it to the power of t. Yeah. Okay. So this is the idea of discounting. What we're seeing here, where we discount past rewards or future rewards, and generally with the discount, this is the gamma is a discounting factor, which is always smaller than 1 and bigger than 0 at each time step. So so sooner rewards have higher utility than later rewards. That's the idea. The same with the money, utility of money. So $10 now are worth more than $10 a year later. And again, we visualize it here. So rewards we get here in the very first step will have a value of 1, for example. Then the rewards in the second step will be discounted by gamma. The rewards in the third step will be discounted by gamma squared, and so on. So in our tree, we will keep discounting that. So let's do a recap of what we defined so far. So we defined the states of this an MDP. The starting state is 0. The actions, north, south, east, west. Transitions. If I'm in a, what's the probability of being in state S and moving to state S prime, given that I take action A, or also written as this T of SAS prime. We have rewards of SAS prime and discount factor. And we'll see soon how we'll basically build these quantities in an MDP where we'll have 4 concepts. We'll have a policy. So what are the actions we take at each state? We're trying to learn that. We'll have utilities for each state. We'll have values for each state. So utilities for each state are basically the sum of discounted rewards. And the values will be the expected future utilities from the state. So is that the expected value, the value of being that state, even though it has no, so for example, in our case here, even though, for example, this state has no reward, simply because it's close to the final state, then it has a high value. It will have a high value because you just need to do a small final step to actually get the big reward. So this is the difference between the values and utilities, for example, in that particular state. That state will have a high value, but still no reward. Let's take a break now. I think as we start going into the Bellman equation. So let's take a break, an 8-minute break, and then we'll continue afterwards. And we have a quiz also in the second half of the lecture.
One of them is English, one of them is like the actual file. No, specific annotators, you're right. I'm thinking of that. How do you just go to there's like a table, and then yeah, you put 7 or 8 things on there. I was saying, like, you look like you were in At one point you were just like going on the screen, and now like, yeah.
Okay, shall we get started? So in the process during the break, I realized I can also use this TV to see the chat on Zoom. So I think that might actually be a useful feature. So those of you on Zoom, I can see the chat now on the TV, and if you have any questions during the talk, like you just type them on the chat or even unmute yourself, and I'll be able to see them also there and pick them up. So it's a new functionality I've figured out. So because I wasn't able to see the chat until now, but now I can see it live. Okay. So far we've been defining all these concepts that I hope are clear by now. The next step, in the next like half an hour, 20 minutes, half an hour, we want to find out how do we actually learn a model? How do we learn the policy, the optimal decisions the robot can take at each state? So for this, we're also defining the concept of these optimal utilities And we define the following. So for each state, we define the value of the state as the expected utility starting in the state S and acting optimally. So that will be the value of the state. So it's essentially the expected future rewards we can get from that state. So again, for example, this state would have a high value because in the future we're very close to the state is very close to a state that has a higher reward. This is +1. This state has a much lower value because it's close to a state that has a low reward, like a negative reward, plus it's also far away to get into. For example, here you have to go all the way like this or like that to reach a state of high reward. So that's why that state will have a low value. And then we also define the same concept of a value, but also for a Q state now. So a Q state, remember, it's a tuple of a state and an action. It's the two of them combined. It's a state and an action together combined. So then we'll have the same thing. We have the value of a Q state will be the expected utility starting in a particular state and taking action A, and thereafter acting optimally. And the optimal policy, which we call pi, is the optimal action that we'll take in each state. So pi of S will be what is the optimal action we can take from that particular state. Do we go north? Do we go south? And so on. So notice here how on the right-hand side, well, actually a question for everyone, so including people on Zoom. What's the thing on the left-hand side and what's the thing on the right-hand side? What are each of them?
The left-hand side would be our rewards for being in that state, and then the right-hand side is our optimal action when in that state.
Yes, almost. Yes. So the right-hand side, yes, is the optimal actions we take from that state. The left-hand side is, I wouldn't say the rewards in that state, but the values. So because these states have no rewards, they have 0 rewards. These are different from the values. The values are what's the expected future rewards. So these states, again, on the left-hand side, these have 0 reward. There's no reward. We only get a positive reward here or a negative reward there. So only these states have rewards, but these have values nonetheless because that's the expected future reward of being in that state
and then taking these actions we expect to get.
Yes, exactly. So starting in this state, for example, or starting in this state and taking some actions on some optimal actions, you'll expect to eventually get a utility of 0.8. Starting in this state and taking some actions, you expect to get the expected future reward or utility of it of 0.76. That's what they mean. So the Bellman equations, what they say is that we can do an iteration between these values on the left and these actions, the policies on the right, and we keep iterating between them, and this way we will converge. This is what the Bellman equations will say, like, intuitively. So the optimal rewards will be that we maximize over the first action and then follow optimal policy. So formally, the value of being in a particular state S is we look at the Q states, the values in the Q states. So for all the actions A that we can take starting in state S, we take the optimal action, the maximum, the best action we can take, and that will be the value of being in that state. It's the maximum over all the actions we can take from it. The value of a Q state, the value of Q of S and A, optimal value, so here star would mean the optimal one, would be that, so this is better understood, this equation in blue is better understood by starting from the back. So listen, follow me. So we start from the back, we look just at the last term, V of S prime, this one, we start from here. So to compute the value of the Q state, we start from the value of the states we are right now. We discount them by gamma.
S prime is the state we're heading to, right? Is our target state?
Yes, I'm wrong. Yes, you're right. So sorry, I was wrong. So S prime is the state we end up in. Yes. So I was wrong. The idea is we compute the reward of we in state S and take action A. So we compute the probability of getting into a particular state S prime, and then the reward. We take the reward of landing in state S prime, given we were in state S and took action A. So here, I can actually move my cursor so for people on Zoom to see. So this is what we do first. We compute the reward of being in state S and take action A and landing into S prime. That's the reward. Then we compute the value of being in state S prime, of landing in state S prime. We discount it by gamma. And then we sum over all the possible states S prime we could take. Because we could end up, even though we are in state S and take action A, we can end up in various states. So remember with the robot, even if we are in state 1, and we go north, sometimes we most likely will end up north, but sometimes we can end up also east or west. So so we sum over all the possible states S prime we can end up in and compute the reward and the discounted value of that particular state in S prime. Yes, question.
So the reward can be 0.
The reward can be 0, yes, exactly. This reward can be 0.
And is the transition probability hyperparameter that we defined before we started?
Is the transition probability T a hyperparameter? No, it's not. We have to learn them. We'll see. We don't know them often, so we'll have to learn them along the way.
So we can initialize them.
Yeah, exactly. So,
So if we learn them, like in the grid order example, after a few iterations may learn that when you try to go up, you've got 80% chance of going north, and then 10%, east, and 10% west. That's what the transition probability would be.
yes. So transition probability, again, it's the probability of, even though you are in a state and take an action, sometimes you can. What's the probability of you?
This result taking this action from this state. Right.
Say that again.
The probability of resulting in S prime given you started in S and take action.
Exactly. The probability of landing in a state S prime given that you start in state S and take action A. That's the. Let me see 1 second. Let me see, because I have. This is strange. Can people on Zoom see my cursor? I think so, no? It does look like. But sometimes it disappears. Like right now, yeah, sometimes it goes away. Okay, yeah. So this is how we compute values on the top. This is how we compute the values of a state. This is the values of a Q state now, Q of S and A. And then if we apply them both together, if we combine them, what we get is the bottom equation, which is we simply plug in the equation for Q star in here. So then the value of a state S is the maximum over all the actions. So we use the first part, the maximum over A, of this formula in blue. So then which is the sum over all the possible states S prime we can land into of the rewards of landing in S prime plus the value of the state of S prime, which is now discounted by gamma because it's a step. So notice now how these the equation for these values appears again at the end. So the same values that we're defining V of S appear here for a different state now, but it's the same structure, the same construct. So what this suggests we can do is that we can do an iteration. We can do what is called a value iteration. We start with some initial values for V. For example, they're all 0, for example, and we keep iterating. We apply this equation once, we do an update, and we get new values for V, and then so on, and we get the new values for V, and we keep iterating. This is what is called value iteration in reinforcement learning. Question?
Yeah. state means that we already determine the action, but we don't know what state we will end up. So we have action A, but we have to sum up all the states because even though we know the action, we can probably go to other states, and finally the vs the value s, we have to sum up all the A, means that we have summed up all the actions. So we first sum up all the states given the action, and then we sum up all the all the Q given all the actions.
Yes. So let me answer the second question. So yes. So we for a particular action, there are multiple states we can end up in. So we sum all those states with S. That's the summation over S prime. But then we can take multiple actions. We have to take the best action. So we have to compute the best action we can take going north or south. And that's why we do this maximization over A. So we're trying to maximize over all the actions. And try to find the best one. And what was the first question you asked?
It's already solved.
It's already solved. Okay. Any other questions? Is this clear? Yeah, I see some nods. Good. Is it clear on Zoom? You can chat. You can type questions on the chat as well. I can see them live now. Okay. So now again we have the mathematical framework for defining these optimal values. These are optimal values for states, for Q states, and so on. But we need a method, a method for computing them. And we'll see shortly how there's two types of methods. One method is called the value iteration. We iterate over these values. And there's another method called policy iteration, where we iterate over the policies pi. So then both work quite well and have still different advantages and disadvantages. And let's see shortly how we do value iteration. So again, remember we have to find the optimal policy pi, and we have these equations. What we do in value iteration is that we initialize our values with 0, for example, with some initial values, and then we apply the Bellman equation, and that is the Bellman equation that I showed earlier on the previous slide. So we applied this, and now notice the only difference we had from before is that we added these indices. We have these are the values at the iteration I, and if we apply this update, we'll get new values at iteration I plus 1. And we keep doing multiple iterations like this. And then again, we throw out the old V values and so on. And this is called the value update or a Bellman equation update. And we repeat until they converge. And there's a theorem that says, yes, that it will converge to unique optimal values. But yeah, I'm not going into that, into the theorem, into the theory right now. So let's see a visualization of how it works. So in our grid world, so for example, in our scenario, so we start with V1 here on the left side, which is basically all the states have 0 value apart from the 2 states which have the reward. So those will have a +1 and -1. And we do a single update, and then what we get is that this state has gets a value of 0.72. Yeah. We applied this equation once. So basically these values at the end had the value of 0, most of them, apart from this one, which has a +1, and this one has a -1. We discount it by gamma. We take the reward and so on, and then we take the maximum of the equations, of all the action. We compute the differential probabilities, and we take the maximum.
That's applying it once, just to that one state.
Once from here. So let me ask a question. Why doesn't this state have why does this one have a 0? That particular state, which is next to -1. Could it not have a negative utility, for example? Negative value?
Because finally we take the maximum
Yeah, yeah.
I don't. Or maybe the maximum path is 0 other than a negative number. So yeah. So if we calculate 0.
But you were correct. You were correct. It's because you take the maximum action. You take the maximum action like this, moving from this state to -1. So the state next to -1 to moving to actually -1 is suboptimal. But because we take the best action here, this is bad. So it's better to not take that action and stay at 0 or like go up, for example, go north or south. So that's why this doesn't get updated. So only this one gets updated because you take the best action from here is to actually move to the right. Does that make sense?
So every state got updated simultaneously on the first.
Every state got updated in the first. Yes, exactly. All of them we updated one. And look, so we have these. So look at what's been happening now. So we do an update now, another update in computer v2. So this is what happened before, but now color coded. So we compute the value of staying of being in 3-3, state 3-3, as the transition probability. So we sum over all the possible states that we can land to by being in 3-3 and going to the right. So if we are in this state and going to the right, we sum over all the possible states S prime we can land into, and we multiply by the reward of being in 3-3 times the discounted value of that. So that comes to 0.9 times this. So remember, our 0.8 is our probability of actually landing in that state when we go right. 1 is the final reward. And these are probabilities of landing in, even though we try to turn right, we end up, for example, like one way is to end up like north or south. And north, if you bump in the wall, you end up in the same state, so you don't move. So this will be still a reward of 0. This will have a reward of 0 because it's this one. So that's how this works for that example. And look what happens if we do this multiple times. So we update it once, and we get 0.72 after 2 iterations. So we have 2 iterations, and I have v2 now. After 3 iterations, now we get these states to have non-zero values because it propagates. The values propagate from this state also. And then these ones, after another iteration, now it's after 4 iterations, we get more states that have non-zero values. After 5 iterations, we get even more. After 6 and so on. So these ones start getting also like non-zero, and we can run, and then they still converge. You see to again after 12 iterations. So this one still get updates. 0.47 goes to 0.48 and so on. So you see how after we do many iterations, it will eventually converge to some values, each of these states, even though they all come they all come mostly from being in state 0 here or 1 here. And of course this one also takes into account, because sometimes even though if you're in this state, even though you try to go north, sometimes you can end up and fall into the pit, for example, and still end up in the -1 state. So that's why these are lower. These values are lower because of that.
And when we're calculating this for each grid, we can calculate each tile in parallel, right?
Yeah, exactly. We can do all these calculations in parallel. Each of the tiles can be done in parallel. What's sequential about the algorithm is the fact that we have to do these iterations, all iteration for the entire grid.
To grid.
Yeah, exactly. Any questions? Yeah. So I'm going through it again. So let's start from the beginning. So this is the iteration. This is how we start. Yeah. Oh, the equation. Oh, yeah.
So for a given state, suppose 1, 1. So sorry.
This one?
1, 1. So the
Which one? This one here.
The value for, suppose we are taking action now, we go to 2, right?
Yeah.
So value will be 0 and we want
The value will be 0 and
reward, R value.
the R value will be 0, yeah.
So if values after some iteration, value becomes something else, point something. So Vi will become that value and reward will still be 0.
Say it again.
So after few iterations,
After few iterations, yeah.
it becomes Vi will be updated, right? It will be some 0.2 something.
VI will update, yeah, yeah.
So the reward is still 0 or reward is also updated?
It'll take a few iterations before V1 becomes non-zero.
The reward will still be 0 here, but the values, for example, the value of being in this state will become non-zero after some iterations.
So basically reward is 0 for all the cells except those two.
Exactly, yeah,
Every item.
yeah.
Well, so for this one we have living reward is 0. How would it change it if living reward was non-zero?
If the what do you mean, living reward? No.
Yeah, so at the top you have, in the example you said gamma equal to 0.9, living reward equal to 0, and noise equal to 0.2. What if living reward was non-zero?
Yeah, yeah. I think living reward would be non-zero would mean that yeah, these cells will have, like, for example, instead of like a constant like 0.2, either positive, for example, or even negative. You can be like, oh, because you consume fuel, for example, so it can be even slightly negative. It would be a minus 0.05. So essentially, what will happen in general? It will force the robot to find short path solutions.
Or more specific paths based on
More specific paths. Like it will try to avoid long paths, even though they can. Yeah, that's what it would mean. Yeah, yeah.
How would that calculate into this formula?
So this reward here will be non-zero
Okay.
for the states.
Oh, yeah. Okay.
So initially, only these two states have rewards by being into them. All the other states have a
So
zero.
if we had a living reward, then the others do.
Yeah, yeah.
What does noise mean?
Noise means that when we take an action to move north, sometimes we can end up east or west with a small probability, like 0.1 each way. It's and that's why that's why we have this transition probability here, because even though we are in a state S and move north, sometimes we can still end up not actually going north, but going east or west. And this impacts the probability of being in this state, because one second, because then even though you try to go north, you still have a small risk of going east here, and that's why and that's why this has a much lower value than this one here. So this path, you see, this path is safer to take than this path. We had a question.
So do we start from the reward state or do we start from the state before reward state? We backtrack to that.
Do we start from the reward state?
Get the value for each position.
What do you mean by reward state?
No, do we start from the value 1 or do we start from the value before that? That is 3, 4 or 3, 3. Which one do we begin the algorithm?
We start from here, or is that what you mean? Oh, no, and we start, in particular, our robot is in this state, in 1, 1.
I think it means if
What
the
do
How are the values calculated for the last state then? For the
So initially everything will be 0.
okay.
Only the 3, 3 will be updated because its future state has some sort of a value. So
when the robot
initially
reaches 3,
you will calculate the whole grid.
So the value is updated when the robot reaches 3, 3.
Yeah, kind of. But it starts from 1, 1.
So how does it know? which
Because
way to
value will be
go?
0 and reward will also be 0.
So
all values will be calculated, but only the values that close to the 1 or minus 1 will have non-zero value. All values will be updated, but maybe others will still be 0.
yes. So the idea is these we start with all the values being 0 apart from and this is showing the utilities, which also means the expected future rewards. So basically these states have rewards, the other ones have 0 rewards, and values initially are all like this, are all these values. This has a 1, it has a -1, and then these slowly propagate basically to remember our robot starts here, but this isn't like that's actually not important here, like right now where the robot starts. What we're doing right now is we're iterating over the values of the maze, and we're trying to find which states are good states to be in. Like for example, this is a good position to be in.
So what counts as iteration? Reaching the reward or
updating the whole grid, the values for the entire grid once.
So should they travel the whole grid before reaching the reward? So then shouldn't the values be updated before that?
So all the values are updated. All the values, all we update all of them.
So after one iteration, like there should be some value near -1 also, because there would be a chance it would reach -1.
That's what I was trying to explain. This one doesn't change because the optimal action here is, so you don't want to move right. The optimal action is to actually you don't want to move right, and when you try to move north, you still see a value of 0. So that's why this doesn't update. It's only after you see that this state got a value of 0.72, then you realize, oh, if I move north, I can capture this value. That's what is happening. I hope come to my office hours. I can explain in more detail. Any other questions? Any questions on Zoom? None so far. Okay. So this is value iteration. So these values keep updating after many. So this is after 100 iterations they converge. They all converge to these values. So then the very nice thing is that once we have these values for all the states, we can compute a policy, right? We can then decide, what is the best action to take when I'm in this state? Well, you try to you look at for all the actions you can take. You can move north, you can move east, for example. You try to maximize you look at what the values are, and you see, you decide to take the action that maximizes, that captures the maximum value. So in this case, you decide to move north because this value is higher than this one. So that's why you decide to take the optimal action. So this way you can compute actions for all the grids. So you see here for this particular state, it's more optimal to go left than to go right, even though this is closer to the solution, but this is safer to go to. How are we doing with time? I was hoping to run a quiz. Shall we start? Have at least a couple questions? Yeah? Okay, let's do it quickly. Fast quiz. So. Quickly. Yeah. Okay, so join myquiz.com, and this is the code. And so I prepared this quiz also from last time. Well, and I added some more questions, so it will have some boosting questions, of course, about other boosts initially. So, and then there's some questions on RL. that I don't think we'll get to, but we can continue next time. Okay, everyone joined? Almost, I see a few people still. Okay, we'll start, it'll take 10 more seconds. Okay, shall we start? 3, 2, 1. Okay. So remember AdaBoost, how it was working. We were reweighting the points based on the misclassified ones and the correctly classified ones, and retraining. And for each model, we're computing a confidence in the model. 15 seconds. Let's see. Nice. Okay, so let's see what happened. So it reweights the data points to fit a better classification boundary. Is it correct? Yeah, it is. Yes. So remember, we were reweighting in AdaBoost. We were reweighting each data point and refitting the models every time. Since it estimates weights for data points, it doesn't need to estimate weights for classifiers. Is that correct? I see a no here. Are there different opinions? So we actually do estimate weights for classifiers as well. These are the confidence scores. So in AdaBoost, is that? Yeah. So remember, in AdaBoost, we were computing these weights for the data points, for each data point, whether they were misclassified or correctly classified, and also these weights for each classifier method, these confidence scores alphas. So it does have weights for each classifier, and these are the confidence scores. And this tells how good the classifier was overall at computing, making predictions. Learners can be any models. Is that correct? Yeah. Yes. So any models, we can apply AdaBoost with any kind of model, linear regression models. We can do decision trees. We can do SVMs. Any kind of decision models can be a learner. It is highly prone to overfitting. It's actually quite robust. In general, overfitting does happen, but it's actually much more robust than other methods to overfitting. So AdaBoost. So especially when it uses weak learners, like simple learners, and also if it has it doesn't have too much noise in the labels, but rather noise in the data points. Okay, let's move to next question. We'll do one more and yeah. Okay. Why do unstable methods perform well? 15 seconds. Okay. Let's see. So their biases average out to being accurate. What do we think? Yes. So because each model has different biases, but when they average out, exactly, that's a good answer. Combining a bunch of methods can eliminate problems from a single method. Yes, that's a good take on it. They average the bias of different models. Yes, it combines multiple models together to get a better average. Law of large numbers. Yes. So the law of large numbers, again, this is very much related to that. An ensemble can make better predictions and achieve better performance than any single contribution model. Yes. An ensemble that reduces the variance in the error in effect will shift the distribution rather than simply shrink the spread of the distribution. Wait, let's see what that means. So an ensemble that reduces the variance in the error will shift the distribution rather than simply shrink the spread. Can that person explain a few more details? Who wrote this? Do we actually shift the distribution? So the variance still refers to the spread somehow. So while shifting the distribution still relates more to biases, but I think something interesting here. I'd be curious to hear more on this take. They remove the bias of the models by averaging. Yes. Reduce the variance in error. Yes. This is the variance. Yeah. Okay, so I wish we would do because I had some really nice RL questions in this quiz, but we'll have to do them next time. So we'll stop here, and we'll do the quiz. Yeah, we'll do the questions next time on Monday, and we'll finish with the RL. Okay, have a nice weekend, everyone.
Thank you.